Hello everyone. So I'm going to go over HeapSort in this video. I'll first go over sort of the build heap operation before I cover actually HeapSort. So let's go ahead and dive right into this. So let's talk about HeapSort. So just the first step for HeapSort is the idea is you're given an array. Given an array of size n. You want to sort this array. So the first step is you have to create a heap from the list. Now, is it a min or max heap? So since we're going to be covering sorting an array in ascending order, we're going to be using a max heap. So I'll go ahead and put these two over here. So for sorting in ascending order, so from lowest to highest, then we're going to use a binary max heap. So we're going to be covering this in this video. Now, I guess if you want to sort this in descending order, you would use a min heap to do this, and we'll see why in a second. So basically, remember, we have this operation called build heap. So just kind of recap this. It was mentioned earlier, but I'll go ahead and talk about it again over here. So build heap. Okay. So basically, remember, we have these operations bubble up and bubble down for a min or max heap. I mean, it's the same idea actually for min or max heap, except for min heap, the parent must be smaller than both children, and for max heap, the parent must be larger than both children. So anyway, to do a build heap operation, I'm not going to go over all the details in this video. I don't want to make this video too long. It might be long because I do ramble a lot. But for a build heap operation, here's how we do this. So remember, we have this heap sort of stored in an array, and we sort of visualize it as a binary tree. So to do a build heap operation, all it takes is really just this. So we have a for loop for int I equals 0, I less than, I guess, the size of the heap. So I'll go ahead and I'll use size right now. So size denotes the size, how many elements we have in our binary heap. And then, I made a mistake here. It's supposed to actually be I equals size, and I is greater than 0, I minus minus. There we go. That's the correct way of doing this. And then we go ahead and call bubble down, and you pass in I. So bubble down would be a heap function, and it takes an argument. And the argument really is, I want to bubble down from index I. So you pass in some index, and it's going to bubble down from this index. And this operation itself is going to, in fact, create a heap. So if you do a max heap, then this bubble down operation, bubbling down from the leaves upward, will actually create a min or max heap, depending on which one we're trying to actually do. Now, I can't really cover the math over here, but this operation overall, doing a build heap operation, does take O of n time to do this. It does seem kind of weird, but if you want to know why, you can always ask me, but that is the rules. In this case, in this video, I don't want to make it too long. You're going to have to kind of just believe me here that this operation does in fact take O of n time. That's your first step. And once you have your heap created, then, so if you want to sort in ascending order, I have a max heap. Basically, after this, all I have to do is constantly, so basically just call delete max, this delete max function, call delete max function, n times. That's really all there is to HeapSort. Now we'll go over actually all the details for all this in a second, but that really is all there is to this. So you first create a heap, then we call delete max many times, n number of times, because n is the number of size of elements you have in your list. So you can already see right here what the runtime for HeapSort is going to be, but of course I'll explain it in a second. But let's go ahead and do an example here. So let's go ahead and do an example, and I think that might actually help understand. Also, I'll talk about how this example, how on the exam this question would sort of pop up. So let's go ahead and create sort of a random list. given to us initially. So I'm going to go ahead and do the following. I'm going to cheat here and just paste this array here. I don't have to like draw this whole thing out. So let's say we're giving an array. So let's say we have 3 over here. I'm going to put maybe 7 here, and then possibly 2. Then I'm going to go ahead and maybe put in, let's say, 8 over here, and 6. Then we'll have, let me see, we'll have maybe 9 and 10. So there's our initial list given to us. It's definitely not sorted. So let's go ahead and use this sort of list over here. So in this case, well, the first step, you have to go ahead and call build heap to create a heap out of this. Right now, this is definitely not a min or max heap for this matter, because, well, if it was a min heap, the smallest element would have to be at the front. So really, this is not a min or max heap. So since we're going to be basically doing, how should I say, we're going to sort this in ascending order, we want to create a max heap out of this. So basically, I'm going to go ahead and draw the tree here, because I think using a tree is definitely a lot more simpler to visualize than the array. Now, of course, if you were to code this, you would use the array version to, you know, traverse and do all your bubble ups, bubble downs like that. But let's go ahead and sort of draw the tree over here. So if I took this array and I constructed a binary tree out of it, we had the following binary tree. So you have 3, 7, 2. We have 8, 6, 9, and 10. So we have these elements right there. So this is basically, we don't construct this, we just kind of use this to help us, to aid us here. So bubble down, so do a build heap, we just bubble down from the leaves basically. It's okay, let's bubble down from element 7. So index this element here, bubble down 10. Well, we're done because there's no children, it's a leaf node. Let's bubble down 9. Okay, we're done. Bubble down 6. We can't bubble down 6 because there's no children. And same thing for 8. So this bottommost level, we're done. We bubbled down all those nodes right there. So congrats to all of us for doing that successfully. Now, let's go ahead and bubble down from 2. So you first basically bubble down from the very bottom level, from the rightmost. You bubble down this node, this node, this node, this node. Then you bubble down from this node. Okay, so you want to have a max heap. And from this situation here, obviously it's not a max heap because the parent is smaller than both children. So we swap with the bigger child. In this case over here, it looks like the bigger child happens to be this element 10. So we basically just bubble down. We sort of take this 2, move it down over here, and a 10 sort of moves up. The standard bubble down sort of operation. Okay, now let's bubble down this node. Okay. Well, we see here that, well, in this case over here, it has 2 children. This child is smaller than 7, but this child here is bigger than 7. So we have to bubble this 7 down. So we swap the 7, and the 8 moves up. So right now, from this bubble down operation, all we did was we bubble down from these nodes, then these nodes. So basically, in our binary sort of tree here, everything is in heap order except for the root. But up to this point here, all of these elements are in max heap order. So we're good so far. But now we have to bubble down from the root, the last sort of step here. Okay, so from this case, we see that both children are bigger than 3. But of course, we pick the bigger child of the 2 and swap with that. So it's really the same idea as a min heap, except in reverse, or in opposite in a sense. So the parent has to be bigger. So if you want to do a bubble down, we have to swap with the bigger child. In this case here, 10 is the bigger child than 8, so we swapped the 3 with the 10. So 3 goes over here, and 10 moves up. And of course, we have to keep on bubbling down potentially in the worst case, because we have to make sure we are in heap order. So we see here that, well, looking at 3, the right child of 3 is going to be 2, so we're good there. The left child of 3 contains a 9, which is bigger than 3. So we have to bubble the 3 down to the left side of this tree. So 3 goes over here, and 9 goes over here. And a 3 can't bubble down any further because now we're at a leaf node. So let's go ahead and take this tree and draw the array now. So if you were to code this, you would actually have to use the array and do all that stuff here. But I like to use the tree because it's kind of, I guess in a sense for me, easier to visualize when I use a tree when I do all this. So for the exam question involving heap sort, you have to first give me the array after doing this build heap operations. Let's go ahead and draw the array given this sort of tree over here. I'm going to go ahead and sort of paste right here. Awesome. So then let's draw the respective array for this tree. So we'd have 10 over here, then 8, then 9, then 7, then 6, then 3, then 2. So this would be the array after we do this build heap operation. That's how an array would look like. So on the exam, I would have maybe like several sort of, how do you call them, short little answer boxes, if you will. You gotta put these numbers in there. So I would give you like, so I would have like 7 little fill in the blank portions. You gotta put in 10, 8, 9, 7, 6, 3, 2 in that order. You have to put that in there, so it will automatically grade with that. You can of course use paper and draw this out, but you have to give me this array in the first. That's your initial steps. You first have to create a heap out of this. Let me make sure I did this correctly. So 10, 8, 9, 7, 6, 3, 2. Okay, so that's definitely correct. Okay, so now we have our initial max heap. Now we can finally begin doing heap sort. So the first 10 minutes of the video was sort of talking about I don't even know what, but now it's time to actually talk about the algorithm. So the first step is we're going to have a variable. I would declare some variable. I'm going to call it max for right now. And we're going to call a function called getMax. So getMax function is very simple to write because really for a binary max heap, the index 1 is going to contain the max element. So it would be just simply return 1. Now I'm going to also put here, so I'm sorry about this, I'm going to go ahead and put this size variable to be 7. That means we have 7 elements in my binary heap. So we can see here, elements 1 through 7, 7 elements. So we're good. So now we're going to go ahead and call getMax, and max is going to store the value 10. Because 10 is the max element in this structure, because of course index 1 always contains the biggest element. Great. And now we're going to go ahead and call delete max over here. Delete max will be called next. So what does delete max do? Well, we already know what it does. It's going to take the last element in our structure, index 7, because size contains 7, that's the last element, and we're going to assign it to the front. But I'm going to actually not mess with this. I'm going to go ahead and copy this below. So the first step in your algorithm is you want to first have this. And next step, I'm going to go ahead and just sort of move down over here. I'll sort of rewrite all that, I guess. I'll put the whole thing here. So 10, 8, 9. Okay, I'll write this whole thing over here. Perfect. 10, 8, 9, 7, 6, 3, 2. Okay. So when I call delete max, what it will do is take this 2 and overwrite into the very front. So I'm going to go ahead and just do that. Overwrite this and put the 2 over there. And size, well, size of course was 7. But after we do this operation, size will now be 6 because remember delete max, it puts the last element to the front, decrement size by 1, then it will bubble down from index 1. So I'm going to go ahead and draw the array, or draw the tree here, sorry, to represent this array. So in this case here we have, well, we have 2, 8, 9, 7, 6, and 3. Now even though 2 is in this array, it's not part of the heap anymore. So this 1 through 6 is part of my heap, and this element here is now officially gone. So we have 2 up here, we have to bubble this 2 down. So of course, if we do this, well, 9's a bigger child, so we swap with that. 2 goes here, 9 goes up top, and of course, since 2 is less than the child again, we swap it down over here. So this would be the state of our sort of heap. So let's go ahead and draw the array for this. So now in this case, I'm going to go ahead and put the respective array for this. I'm going to go ahead and sort of paste this. So I'm going to do that just to save a little time. So we have 9, 8, 3, 7, 6, and 2. And this spot here we'll leave it vacant for right now. So what's going to happen is, well, the size right now is going to contain 6. So after we do all this, we again have a heap once again. So I'm going to assign the max from the last step, which is right here, contains a value 10. I'm going to store that into position size plus 1. So size is 6, size plus 1 is 7. I'm going to assign the max value of 10 right over here. So I put that in green for a reason, because this is not part of my heap. This is part of my sorted array. So 1 through 6 is my heap, and everything beyond element 6 is my sorted array. It's not sorted the whole array so far, but this is my sorted subarray. So for the exam, on the exam, you have to first, let me go ahead and put this here. You first put this for your answer. And then for the next, the next array on the exam, you'd have to write this. That's your result after doing one step of HeapSort. And of course, we're not done. We have to continue. So let's go ahead and continue with this operation. Let's continue with this. So next step, we do exactly the same thing. We just go ahead and just, we have our max variable here, and we call getMax once again. And since in our max heap, index 1 is my root, the max element will always be at the root. So max, I'm going to store this variable, this value 9 into this variable max. And then I call delete max. What this will do is, of course, it's going to take, I'm going to go ahead and probably just maybe copy this down over here so I don't mess with that array. I want to keep that there for right now. I'm going to go ahead and paste this over here. So I'm going to go ahead and sort of use this array here to mess with it. So I'm going to have 983. And then we have 762. And then we have this 10 over here. So when I call delete max, let me make sure I'm consistent with this picture up here. I modify it here. Okay, so when I call delete max, then size becomes officially 5. And then what's going to happen, we take this element at the very end of my array. So before I decrement size by 1, I first take this value 2 and replace it with the root, and then decrement size by 1. So size will now be 5. And the root now is going to have 2 instead of 9. But we save 9 in this variable right there. So we have that stored somewhere in the variable. So cool. Let's go ahead and now, work with this again. So our tree looks like this at the moment. If we take this array and sort of visualize a tree out of this, we have 2, we have 8, 3, 7, 6. Now, once again, the size is going to be 5. So 1 through 5 is part of my heap. 6 and 7 is not part of my heap. So 2 is not in the heap. And you can see here there is no 2. We only have that root of 2. So you have to go ahead and bubble down this 2. So we see here, in this case, both the children are bigger than 2, but we picked the bigger child to swap with. So I go ahead and sort of swap this 2 with the 8, like that. In this case here, the very next level, I have to continue with this. So after I swap the 2 and the 8, I have to keep on bubbling down this 2 as far as possible. We see here that the 2 children are both bigger than 2. So I go ahead and pick the bigger child. So I pick 7. Like that. So I only have a tree here because it's a lot more simpler to visualize this. I mean, I could have used the array and sort of, drawn arrows on the array instead, but using the tree is much more simpler to help us visualize. So I'm going to go ahead and convert this updated tree into an array. Let's do that right now. I'm going to go ahead and paste over here. It worked just perfectly. So 8 goes up top, then we have 7, then we have 3, then we have 2 and 6, and then this 10 is still here. And then size right now will contain 5. So after doing delete max, the next step is we're going to assign the max from the previous step and store it into size plus 1, which would be 6. So last max, I believe, was the value of 9. We're going to store that right over there. So now in this case, well, now we have the next step. So basically on the exam, you'd have to write this array. That would be your next step, because this is going to be the current state of the array after 2 steps of heap. So after you do your build heap, we ran 2 steps. This would be your resulting array after 2 steps. This part here would be your heap, and these 2 parts here is going to be your sorted array. So obviously we can go ahead and continue some more on this. Let's go ahead and sort this entire array out over here. So anyway, next step, once again, we do the same exact thing all over again. We have our max variable here. We call get max, which once again, the max element in this heap from 1 to 5 is going to be 8 because, well, obviously a root always contains a max value. So we store 8 into max. Then we call delete max, which was going to wipe out that max value. And for delete max, remember as always, you take this value at index 5 and override it to the front and decrement size by 1. So I'm going to go ahead and decrement size by 1 over here to make it 4. And I'll redraw this array, or I'll re-put over here so we don't mess with this example. We don't mess with this array. I want to keep that there. So in this case over here, I'll rewrite this. So we have 873. I'll just do like this. So 8, 7, 3, 2, 6. And then we have these sorted parts right there, just like that. So I call delete max. Well, I'm going to take the last element in the array at index 5 because size is going to be 5, as we can see here. Oh, sorry, size is 5, but after we do delete max, we take the element at size at index 5, put it to root, and then decrement size to make it 4. Okay, so now we overwrite this 8 with the value of 6 and decrement size by 1. So elements 1 through 5 is part of my heap. Oh, sorry, 1 through 4, because size decremented by 1, size became 4 now, sorry. So 1 through 4 is part of my heap. Everything after index 4 is not part of my heap. Let's go ahead and draw the array for this, and then go ahead and go through the whole bubble down fiasco here. So we have 6 at the root, then we have 7, then we have 3, and then we have 2. Now 6 is still in this array, so is 9 and 10, but they're not part of the heap. Elements 1 through 4 is part of the heap, so we only represent these guys in our tree. Let's go ahead and bubble down this 6. So here, 6 is bigger than 3, but not bigger than 7, so we have to bubble it down because the parent has to be bigger than both children for a max heap. Bubble it down, 6 over here, 7 up top. Then we continue bubbling down from this point, but we see here, like, well, we can't bubble down because 6 is bigger than 2, so we're done. We got lucky. That was a very simple operation. Let's go ahead and take this tree and draw the respective array for this tree. So I'm going to go ahead. I think I'm a little bit not really 100% lateral with that, but it's okay though. No big deal. So we're going to have 7 up top, then 6, then 3, then 2. And in our array, we had 9 and 10 here sorted. So after we're done with this, well, size is still going to be 4. That didn't change. Size is still 4. So now I'm going to assign the max from the last step and assign that into position size plus 1. So last step, we obtained max to be 8. So I'm going to store the max into size plus 1, so into 4 plus 1 or 5. I'm going to store 8 right over here. And we can see here, well, we are progressing. We are having a sorted list so far, but it's not all sorted just yet. So we have to continue with this. So I'm going to go ahead and do this video again and again. I'll keep doing this example again and again. I'll go over runtime analysis at the very end of this video and sort of do a little recap of what you want to put for the exam, but let's go ahead and continue with this. So I'm going to again do the same step, max. I'm going to go ahead and call get max. That's going to give us the value of 7 because that's the max value in this sort of heap here. Then I'm going to go ahead and call delete max next. I'm going to go ahead and sort of copy this array here first. Then I'm going to go ahead and sort of explain the whole concept. So we have 763. So let me just make sure I get this here. 763. 2. And then we have 8, 9, and 10. So I call delete max. The first thing that will happen is I'm going to take the element index 4 and assign that into the root. That's the first step, as always. So I'm going to wipe out the 7 and assign 2 over there. And I also decrement size by 1 to make it 3, which means now elements 1 through 3 is part of my heap. 4, 5, 6, and 7 is not part of my heap. Okay, let's go ahead and draw the tree version of this array to help us do this whole bubbling down sort of thing. So we have 2 at the very top, then we have 6, then we have 3. So these elements here is part of my heap, so I draw the tree for this. As I bubble down this 2, so since both are bigger than 2, I have to go ahead and swap with the bigger child, so 6 is the bigger child clearly over here. So I bubble down this 2, like that, and I can't bubble down any further, which means now we're in max heap order. Let's go ahead and draw the respective array for this particular max heap. So in this case now, we have 6, 2, and 3. And this part here will contain, make sure I get this correct, so 8, 9, and 10. Like that. And then we have to go ahead and store the max we got from the last step and store it into size plus 1. So I'm going to go ahead and put the size over here once again to remind us. The size is, in fact, 3. So I want to store this max value into size plus 1, so in 3 plus 1. So index 4, I want to put the max. What is the max variable? Well, it contains the value 7 from last step. So I assign 7 right over here. And, so far, so good. We have, we're progressively sorting this array. It's not sorted yet, but we're definitely getting there. I mean, we have the first 4 done, so you have to go ahead and do the last 3. Okay, so once again, let's go ahead and do the same steps all over again. Let's do the same thing. Let's just go ahead and, go through the motions again. So, max, we go ahead and call get max once more. That's going to store 6 into max because index 1 is the root, and that's the max element. Will be always there. And then we go ahead and call delete max. And what delete max does is, well, it's going to take the element index 3, because size contains 3, the last element in the heap. I'm going to overwrite that into the root, and then decrement size by 1. I'm going to go ahead and sort of draw this array over here again, so we can kind of maintain the last one, just because I want to sort of recap all this at the very end. So I'm going to have 6, 2, and 3, and then 7, 8, 9, 10. So when I do a delete max, the first step is I'm going to take the element at index 3, because size contains 3, and take this and overwrite the root with that. So I take this element, overwrite the root, and then decrement size by 1. So size now is going to be 2. And then we have to bubble down from index 1, which would bubble down. Yeah, that's the whole purpose of delete max. We put the root, and we bubble this new root all the way down. So in this case over here, the size is going to be 2 now. So we have 3 and 2 in my heap, because elements 1 and 2 is part of the heap. And we don't need to bubble anything down, because we're already in heap order. So that was actually really easy. So that was nice. Let's go ahead and draw the respective array for this, which is going to be a little shocking here. What's going to be the result here? We're going to have basically 3 and 2, and then we're going to assign the rest. We have 7, 8, 9, and 10. And then size is going to contain the value of 2, because that's going to be how many elements we have in my heap currently. And we're going to store the max from the last step, which was 6. We're going to store this into position size plus 1. So store it into 3. We put 6 right over there. And that's going to be our result right now. I'm going to recap all this at the very end. Let's go ahead and finish the example off. I want to try to go a little faster here. So once again, we do a max. We call get max. It's going to assign it 3 because 3 is the max value. Then we call delete max. What delete max does is going to take the value at the end of the heap and assign it to the root, decrement size by 1. Let's go ahead and do this kind of quicker, so I don't want to spend too much time. I'm already a half hour in almost, so I'm going to try to speed this up a little bit. So we're going to have 3, 2, and then we're going to have 6, 7, 8, 9, and 10. So we call delete max. What's going to happen is we take the element at the very end of my heap, so size is 2. So take the size index and overwrite the root with that. And decrement size by 1 to make size now will be 1 officially. So in this case over here, let's go ahead and go through the motions. So our heap will be just 2 with no children. And I think we're in a heap order, right? We can't bubble down this 2 because there's no children here. So we are done. That was a very simple one. So now let's go ahead and sort of do this example. Let's go ahead and finish this step here. So now we're going to have the following. We're going to have 2 in my heap, and we're going to have 6, 7, 8, 9, and 10. And then the next step, so remember, size now is going to be 1. I'll write that over here as well. So size will be 1. So we take the max element, that variable we have, some local variable called max, and we store that into size plus 1. So the max value we had in the last step was 3, as you can see up there. So we're going to store 3 into position size plus 1. So we're going to put 3 right over there. And we're not done because once size is 0, then we officially stop this process. So let's do one more step here. So let's go ahead and do the last step. We're going to go ahead and call, so we're going to have our max variable. We're going to call get max, which will return the value 2, store into max. And then we're going to call delete max. Okay, so let's go ahead and redraw this array over here at the very bottom. Let's redraw this whole array brackets. I don't want to mess up that example right there. So we have 2. Then we have, try to see if I can put this here. So we're gonna have 3. What else we have? 3, 6, 7. Okay, 3, 6, 7, 8, 9, and 10. So what does delete max do? Well, it's going to first take the element of position size, index 1, and overwrite it with the root. So we're going to overwrite this 2 with 2. That's kind of strange, but yeah, that's in fact what will happen because we overwrite element with size. We're going to overwrite that with the root. And then we're going to, well, decrement size by 1 to make it 0. Now let's go ahead and draw the heap and binary tree form. Yeah, there's our tree right there. You can probably see it right there. It's definitely there. So we're done bubbling down in this case because it's an empty heap now. So obviously there's nothing to really draw here. So let's go ahead and just copy this array over here. So we're going to basically have 3, 6, 7, 8, 9, 10. And the size now is going to be 0 because there's no elements in my heap anymore. So the last step is to store the max in the previous step and store it into size plus 1. So the max here is 2. So we're going to store it into size plus 1. So size is 0 plus 1 is 1. I'm going to store that max right over here. And now we see every element is in green, which means that it's sorted. But in reality, once the heap is empty, so the heap size is 0, we have our array sorted. And we can see here, definitely sorted. So for the exam, I'm going to go ahead and sort of highlight this right now. Here's how the exam has to go. So I'm going to try to zoom out over here a little bit so we can kind of see everything. So this example here, on the exam, what you'd want to do is you're given, let me see, let's try how far do I have to go? Jesus, okay. Okay, so the first step is you're given this array. So here would be your initial answer. I'm going to go ahead and put this here, maybe in this space. I'll use a rainbow color. So this would be your first array you want to sort of draw. That's going to be the array after you do your build heap. And then on the exam, I'm going to give you a set of sort of text boxes to write your answers. So this will be your first answer. You got to put in 10, 8, 9, 7, 6, 3, 2. That'll be your answer for the first step in a sense. And then this would be your next step. You want to sort of put this on the exam. This would be the next answer. So after you one step of HeapSort, 9, 8, 3, 7, 6, 2, and 10. That would be your, you got to put this answer into the text fields in the exam. And then the next step would be this. You got to put this, so you maybe on paper on the exam you can kind of draw this whole thing out, but you want to put this answer in. That will be the next array you want to sort of have. And then after that, this would be the next one. That will be your next answer you want to put into the exam sort of text field area. and then it would be this one would become next. This is the next one right here. And after that, let's keep continuing here. So this will be your next one, next array you want to write. Then you have to sort of put this over here. And even though it's kind of, kind of redundant, you would have to actually put this, because that would be the final answer, because you'd have to do one more step you'd have to still run. So you want to, unfortunately, it's kind of silly to write the same thing again, but you'd have to do that again on the exam. So it's kind of the unfortunate thing. I can try to export these notes, but if I try to export these into PNG, it might be very pixelated, so it might not come out very well. But I'll try to export these and see if it comes out okay. But that's basically HeapSort. Let's go into a little bit of analysis here for runtime. So basically, HeapSort really is, so let's go ahead and put this here. So runtime analysis. So really, HeapSort is really just an enhanced version. Of selection sort. Because really, we are constantly finding a max and putting it at the end. Find the next max, put it at the end. We're doing that again and again. But with selection sort, it would take O of n time to find that max over and over again. But for HeapSort, well, find that max will take log n every single time. So we already kind of have an idea of the runtime, but let's go ahead and just, just for a sake, let's go ahead and talk about that. So for runtime, the first step is you go ahead and do a build heap. That's our first step when we do HeapSort. And as I already told you, it runs O of n time. I can't prove it here in this video, but it does run O of n time. So when you bubble down from the leaves upward, which is the very first part of this video that I did, that took O of n time to do. Perfect. Then we have to, sort of run the steps of HeapSort, if you will. And what would this runtime be? Well, let's go ahead and first guesstimate this, and then let's go ahead and do a better math analysis. But the idea is we're going to basically, in a sense, so when we do a get, so when we do a get max, that takes O of n time to do that. Oh, sorry, O of 1 time. So get max is O of 1, because really we return the value at index 1 in my array, and that does not really matter how big the array is. It's going to be O of 1 no matter what we do. Then delete max, as we know from before, from previous lectures, it takes O of log n time to do a get max. So we have to do, basically, we're going to do, we're going to sort of do this delete max function, delete max operation, n number of times. So we can guesstimate this. So each delete max takes O of log n. We do this n number of times. So we do this O of log n steps n times, so n log n. But a better way of analyzing this really is, well, when we do a delete max, the first time we do a delete max, it will take log base 2 of n. If we do delete max again, we're going to do log base 2 of n minus 1, because we have one less element in our heap. Then we do log 2 of n minus 2. And then we keep doing this until we have one element in our heap. So then we do log 2 of 1. And this summation from previous lectures, you already determined that this is going to basically be log of n factorial, which is going to be also O of n log n. So this operation, doing these HeapSort, all the HeapSort steps will be collectively n log n. So then we have this build heap, O of 1, plus this n log n, because really, every time we do this, really doing the get max, and if you store that max element into size plus 1, that's also a constant runtime. So the real work of this really is that bubbling down part, delete max. So it's O of 1 plus O of n log n. Therefore, the runtime is going to be O of n log n. So I'll put this over here. That is the runtime for HeapSort. So now you're probably wondering, well, remember how we talked about build heap before? So if I'm given an array, I could one by one insert into another array that represents a heap, and I can create a heap essentially in O of n log n time. So if I take every element from my original array and one by one insert into another array, this other array would be my max heap. That's n log n. So if I had O of n log n, and plus O of n log n, it still is O of n log n. So why do we even do a build heap operation? Well, one thing is that, well, it's not asymptotically better, but overall, O of n plus O of n log n is a little bit better than having 2n log n. A little bit, not asymptotically better, but a little better to use this approach. Also, we don't have to create a second array, which we save a little bit of space. We don't save asymptotic amount of space, but we save a little bit of space. So that's kind of the few reasons why we do this build heap first. And of course, the real reason is because to make the exam question just that much harder, because of course it's a little confusing to do a build heap, and we can't make life easy for CS students at UNLV. So, but the idea is follow these steps on paper during an exam, and then after every step I highlighted, you put that array into the Canvas exam area. So that's basically build heap and heap sort. Hope this video did explain everything. If you have any questions, of course, you can always send me a message on Discord and whatnot. But I think that'll be, I did 40 minutes of lecture there, so I think I'm going to go ahead and stop here. So take care, and yeah, stay safe.